Kinematics practice problems number 3. Bob leaves home at 9:10 and runs at a constant speed to the lamppost, which, if you couldn't tell, this is my beautifully drawn lamppost. He reaches the lamppost at 9:12, immediately turns and runs to the tree. Bob arrives at the tree at 9:15. Part A, what is Bob's average velocity in meters per minute during each of these two intervals? And part B, what is Bob's average velocity for the entire darn run? Okay, the only equation we're going to need in this problem is our definition of velocity. So what is our definition of velocity? Our definition of velocity, average velocity, is delta x over delta t. Meters per minute, miles per hour, whatever, which equals x sub f, our final displacement, minus our initial displacement, over delta t, which is just our final time, minus our initial time, of course. So for part A, which we're going to tackle first, obviously, Bob leaves home at 9:10. So Bob leaves home, he's flying, at 9:10. So he starts at x sub I, initial displacement equals 600, and he goes to the lamppost, and it takes him 2 minutes. Let's write that down in terms of math. How long does it take? V bar, now I'm just going to make it 1 for our first interval of the trip, equals x sub f minus x sub I. X sub f, he ends up at x equals 200 meters. 200 meters. And of course, he starts at x sub I equals 600 meters, minus 600 meters, divided by t sub f, 912, minus 910. And of course, you could have just written 912 minus 910 equals 2 minutes. Or you could have just looked at it for a second and said, hey, that's 2 minutes, but I'm just writing it out this way. So this simplifies down to V bar 1 equals 200 minus 600, which is negative 400 meters, divided by our 2 minutes, of course. And dividing this, we get V bar 1 equals negative 400 divided by 2, which of course is just going to be negative 200 meters per minute. There we go. That's our first answer for the first interval of our first part of this question. For the second part of this question, what happens? Well, he reaches the lamppost at 9:12, immediately turns and runs to the tree. Bob arrives at the tree at 9:15. Okay, so during this interval of the trip, he starts at 9:12, he gets there at 9:15, he's running for 3 minutes. So in terms of the math, we have V bar 2 equals x sub f, which is just 1200 now, 1200 meters, minus where he started from in the second interval, which is the lamppost, 200 meters, divided by, I'm just going to say 3 minutes, 3 minutes, which equals 1200 minus 200 is 1000 meters, divided by 3 minutes, which simplifies down to 333.33 meters per minute. Beautiful. Now notice how in the first interval of this problem, Bob has a negative velocity. Why is it negative? Well, he's running from his home to his lamppost, and he's running in the opposite direction of the positive numbers in our coordinate system that was given to us. We could have said our 0 point or our origin was at the house and scaled everything relative to that. So I'm just going to write my answers over here so we remember them. All right, on to part B. What is Bob's average velocity for the entire run? Well, we are just going to be using this equation yet again, solving for our average velocity, V bar. So let's figure out all of our values. Now remember, Bob starts at 600 meters and he is going to end after the 2 intervals at the tree, which is 1200 meters. And how long does it take for him to do it? Well, he starts at 9:10 and he ends at the tree at 9:15. 5 minutes. Delta t is just 5 minutes. Of course, just to be rigorous about this, delta t equals tf minus ti which equals 9:15 minus 9 o'clock. So of course, delta t is just 5 minutes. Very good. Now, plugging in our other values, we have v bar equals x sub f. So our final displacement, 1,200 meters. And our initial displacement, which was 600 meters, 100 meters, all divided by our delta t value, which is just 5 minutes. 5 minutes. V bar equals 600 meters, which is just 1,200 minus 600, over 5 minutes. And if my mental math serves me correctly, this is just going to reduce down to 120 meters per minute. So we had two separate parts of this problem, and they both evaluated the different things. Of course, each part was a little bit different, but this kind of gives you a guide on how average velocity is really kind of arbitrary or relative, I would say, based on what the problem is asking. Because during the entire trip, he was going 120 meters per minute, and if you break it down into each segment, we get two entirely different answers. Okay, so here's our problem. A particle starts from x naught equals 10 meters at t naught equals 0 seconds and moves with the velocity graph shown. Part A, does this particle have any turning points? If so, at what time? Part B, what is the object's position at t equals 2 seconds and 4 seconds? So obviously we're going to tackle part A first. Does this particle have any turning points? Now, what is a turning point? In terms of a velocity versus time graph, a turning point is any moment where the velocity goes from negative to positive or positive to negative. So just based off of that, we can see that velocity is negative here, it turns positive here, so therefore our turning point is going to be where it crosses this x-axis or time axis at t equals 1. But what is a turning point intuitively? And to answer this, let's just pick an arbitrary origin and call it right here. So we're not talking about the problem right now or anything, we're just talking about turning points. And say I pick an origin to be right where I'm standing right here and define a positive displacement to be in that direction and define a negative displacement to be in that direction. So if I'm moving in the negative direction, my velocity is going to be negative. And a positive velocity would be when I'm moving in the positive displacement direction, which I've defined to be in this direction. So if I'm moving this way, my velocity is positive. So in terms of the graph, what does this mean? For the first second, from 0 to 1, I have a negative velocity that's going up at a constant rate. So that means I'm going in the negative direction. And then my velocity is going to decrease until it hits 0 at 1 second. And then it turns positive because it's above this x-axis, which is just the time axis. So at this point, I go from moving this direction, 0 meters per second, and then I start moving in this direction. So that's kind of why it's called a turning point intuitively, because you're literally turning direction in which you're moving. So just to write this answer on the board, part A, yes, at t equals 1 second. Nice. Okay, what about part B? What is the object's position at t equals 2 seconds and 4 seconds? Now, let me write down the definition of velocity to answer this question. Average velocity is equal to delta x over delta t, distance over time. Nothing crazy here. And this ends up turning into x sub f, final displacement, minus initial displacement over final time minus initial time. Literally the definition of velocity. And in your textbook, you find that x sub f is equal to, which is the same thing as this x sub f is equal to x sub I, our initial position, plus, and I'll use a different color to show this, the area under the velocity curve. And this has to do with calculus, which you don't have to necessarily understand yet if you're in high school or early college physics, but intuitively, that's what x sub f, our final displacement, is. So let's quantify this in terms of part B. What is the object's position at t equals 2 seconds? Well, that's going to be right here. And if we want x sub I plus the area under the v curve, the first thing we're going to want to do is figure out what the area under this curve is. So this area under the curve is equal to this area plus this area. All right, not too bad. So we can literally just calculate this via geometry. So I'm going to call this A1 and this A2. A1 is equal to 1/2 base times height because that's just the area of the triangle. So this equals 1/2 base, which is 0 to 1, which is just 1 second, times the height, which in this case is 0 to -2, which is -2 meters per second. And of course, this evaluates to 1/2 times 1, which is 0.5 times -2, which is -1 meters. And notice how seconds and meters per second, the seconds cancel in terms of the units. Even the units cancel to just give us meters. So next, what's our A2? A2 is equal to area of the triangle, 1/2 base, which in this case is just 1 to 2, which is just 1 second, again, times the height, which is 2 meters per second, which is the same thing as this, except the -2 is just positive, so it's just 1 meter. So, adding these together, A1 plus A2 equals -1 plus 1, which of course equals to 0. So what does this tell us about our final displacement? X sub f equals our initial displacement, which you can't tell from the graph. That just has to be given to you, and it is given to us. X sub 0, which I'm saying is the same thing as x sub I in this case, 10 meters, plus our area under the curve, which evaluated to be 0, plus 0 meters. So x sub f at t equals 2 seconds is just 10 meters. Not bad at all. So now we're literally going to do the same thing, except for t equals 4 seconds. At t equals 4 seconds, and I can illustrate it here, t equals 4 seconds aligns to this final point. So now we're just going to calculate the area of this and the area of this and plug it into our equation and get our answer. Not too bad. A1 we learned from part A. A1 is just -1 meters. And now, same thing, it's a triangle. The area of this, which I will call A2, is just base times height divided by 2. So 1/2 A1 equals 1/2 base, which is 4 minus 1 second. So this duration is just 3 seconds. 3 seconds times the height, which is 0 to 6, which is just 6 meters per second in terms of the graph. So this evaluates to 1/2 times 3 is 1.5 times 6 is 9 meters. So now using this equation, we have x sub f equals x sub I, which again is just 10 meters, plus 9 meters, which of course equals 19 meters. And writing this up here, at t equals 4 seconds, x sub f equals 19 meters. All right, here is our answer. And that's it. Thank you so much for watching the video. Please like and subscribe if you enjoyed what you saw. More problems are coming your way soon. Have a great day.
Run away with me, to run away.